in this goal, we were going to talk about the strength of these intermolecular forces that we've been talking about. And many factors go into determining the strength. So we will first talk about the type of intermolecular force, and then we'll talk about something called polarizability, and then we'll talk about shape or distance between molecules. The closer the molecules are, then the tighter the intermolecular force will hold those molecules, and therefore will be tougher to break them. So the intermolecular force strength is reflected in the melting point. And so the stronger it is, the higher the melting point it will be. The boiling point, the higher the boiling point, that will tell the strength of the intermolecular force. And also higher surface tension, and then the vapor pressure. And this is one trend that's less than the other ones. The tighter the molecules are held together, the lower the vapor pressure. That means it's not very easy to turn it into a gas from a liquid. So again, less vaporization if you have a strong intermolecular force. Okay, the type of intermolecular force. If you're comparing molecules that are about the same size, you can use this as a general guide. So your dispersion forces will be the weakest, hydrogen bonding will be the strongest force, and then you have dipole-induced dipole and dipole-dipole in between. If it is not the same size, then you might have to look up what the values are, and looking up the boiling point can give you a clue as to what is the strongest, because it is possible that there could be enough dispersion forces that can be the strongest intermolecular force between molecules, and even stronger than hydrogen bonding. So again, if it's the same size, you can use this as a general guide, or if you have something bonded to itself. All right, the second concept is called polarizability. And what this means is that in dispersion forces, if there's a lot of electrons involved in the dispersion force, then it's going to make stronger temporarily polar molecules. So remember, dispersion forces, those are between all molecules, but what it means is that the electron clouds shift around. And so in an instant, there might be a little bit more electrons on the left-hand side of the molecule, and the next second it might be over on the right-hand side of the molecule, and then the next second on the bottom, the next second on the top. These are continually shifting. So let's look at two molecules. So we have bromine, and it is a nonpolar molecule. We have two bromines here. And if you look on the periodic table, each bromine has 35 electrons. And so that's a total of 70 electrons. And I'm not going to draw all of them. I'm just going to draw 3 here on each side, so showing that they're evenly distributed. And then we are going to compare this to chlorine. And chlorine has 17 electrons each. It is also nonpolar. And when you look on the periodic table, there's 17 electrons each, for a total of 35 electrons. So again, I can't draw all of those, but I'm just going to draw a couple. But you do know that there's less electrons with the chlorine than you do the bromine. So if we look at a liquid substance of both these bromines and these chlorines, and we look at the forces holding them together, there's only dispersion there. But bromine has more electrons. So what that means is that these electrons can shift over, and when they do this, they can create very large polarity. And again, it's just a temporary thing. They are dispersion forces. They will shift around, and they will only last instantaneously. Now let's look over the chlorine. So there are less electrons over here with the chlorine to be moved around. But if they get stacked up on the other side, we get a smaller polarity. Now let's look at the boiling points of these. So with bromine boils at 59 degrees. And so that high temperature reflects the strength of that dispersion force with all those electrons that are able to shift around. Look at chlorine with much less electrons it boils at negative 35 degrees. So this is called polarizability. Again, the more electrons in the atom, and so your larger atoms are going to have greater polarizability, more so than your smaller atoms. All right, the last thing that goes into determining the strength would be the shape or the distance between the molecules. And the closer the molecules can get, then the stronger those intermolecular forces. And we have two shapes here. Generally, the ones that are long and skinny have greater intermolecular forces, and that is because they can get closer together and they have a greater surface area. Versus if we have a spherical or kind of a balled up molecule, we see that there's not a lot of surface area of where they can attach to each other. And so in this example here, I have my long and skinny one boils right around 0 degrees Celsius. And this other one, the spherical one, it boils much, much lower, about negative 12 degrees Celsius. And so you see that the boiling point is reflected in how strong those intermolecular forces are. So my second one doesn't take as much energy to boil, so therefore its dispersion force is a lot weaker. Versus the long and skinny one, I had to put more energy in there to boil it. And when you boil it, you rip that molecule apart, you break that intermolecular force. So water is a very tiny molecule, but has a high boiling point and a high melting point. Why is this? So if we look at the boiling point of water compared to methane, we see that methane is negative 160 degrees Celsius. And the boiling point of water, that is 100 degrees Celsius. Well, they are about the same size. Why is there such a huge difference in when these molecules will boil? Well, take a look at methane. Methane is nonpolar. Water is polar, and if you look closely, it also has hydrogen bonding. And so when we're comparing the dispersion forces of our methane versus the hydrogen bonding of our water, we see that that hydrogen bonding makes it so it's a much stronger intermolecular force between each water molecule. So therefore, it's hard to rip the water apart. Here's another graph that shows the same thing. So it does this by family. Let's first look at the halogen family, and let's read it backwards. So we have HI, HBr, HCl, and then we would predict that HF might be way down here, but it is up here. And that is because of hydrogen bonding. So remember, hydrogen bonding, those are H-bond bonds. Now look at the trend for the hydrogen chloride, the hydrogen bromide, hydrogen iodide. What's going on there? They're all polar, but how come hydrogen iodide is higher, has a higher boiling point than hydrogen chloride? It is because hydrogen iodide is a larger atom, and so it has a greater polarizability. And so because of that, those electrons can shift over and we have greater dispersion forces. All right, let's look at the other family that's here. This is the oxygen family. Again, we're going to look at this backwards. So looking at tellurium and then selenium and sulfur, and then notice that water's way up there. And it's all for the same reason, the hydrogen bonding, and then we have the greater atom size causes the trend to increase down here. So we have some trends here, and there's really a lot of information here that we can look and analyze. Let's start off with the first row. So this is a row of alkanes. So those little squiggly lines, remember the end is a carbon and any bend is also a carbon. So we're looking at nonpolar molecules in that first row. So this first example, we just have 3 carbons with a boiling point of minus 42, and we add a carbon as we go across this little graph, and we end up with 69 degrees for 1, 2, 3, 4, 5, 6 carbons. So we can see as we add a carbon, we're adding more electrons, we're making the molecule more long and skinny, and so to rip 2 of those molecules apart, they're going to be held really tight with dispersion forces by the time we get over there with the 6 hydrogens. Let's go ahead and look at the next row. So there's alcohols. So everything's the same as that first row, except for we've added this little OH group. So when you look at an OH group, it is oxygen bonded to a hydrogen. So just right on the end. And so we can ask ourselves, is it polar? And we find that it is polar. And then we can also look and see, is there hydrogen bonding? And yes, there is hydrogen bonding between that oxygen, because hydrogen is bonded to that oxygen. So we have both hydrogen bonding and we have polar molecules. And of course, there's dispersion there. Everything has dispersion. But you can see as you add a carbon, you go across, those dispersion forces come into play more. And so by the time you get to the end, you're at your highest temperature. Okay. Now you can compare the two rows. So when I look at 3 carbons without the hydrogen bonding, you can see that it boils quite low. So just adding that little hydrogen bonding with 2 molecules that are very similar, you see that that hydrogen bonding causes much higher boiling points. All right, let's look at the next row, the blue row. These are your organic acids. And so you end up having a carbon chain, and then a carbon is bonded to oxygen, and then another OH group. So we can ask ourselves, is it polar? And the answer is yes, it is polar. And then we can look and see, do I have hydrogen bonding? And you still have that OH group there, so you still have hydrogen bonding. So this is interesting here. We have this little extra polar group here, that carbon and oxygen. So that's what we've added between the yellow row and the blue row. And look at the reflection of the difference in boiling point just from adding that. So it creates a stronger polar bond because it's polar kind of in 2 places. And so that is reflected in that boiling point. We see that as we go down, our boiling point has increased even more. All right, that last row, the orange row, we have some ethers. And what we do is we have a carbon, and I'm not drawing the whole molecule. I'm just drawing the little portion that shows if it's polar or nonpolar. And we have oxygen bonded to carbon. And we can look and see, is it polar? And we find that it is polar. And then we can double check. Does it have hydrogen bonding? And we say no, because the oxygen is bonded to the carbon. Remember, in order to have hydrogen bonding, it has to be bonded to fluorine, oxygen, or nitrogen. So all we have is polar molecules here. So we have dipole-dipole and dispersion forces. And so you can compare it to that first row just up above. We can see how that boiling point drops dramatically. So we see that it is higher than the alkane, the very first one, that is nonpolar, that only has dispersion forces. But our ethers has dipole-dipole, and so it does take it up a little bit, but clearly not as much as that hydrogen bonding. All right, let's look at this bottom example. Why does benzene have higher melting point than toluene? They look very, very similar, but look at the difference in their boiling point. So benzene, or this is melting point that we're looking at this time. So melting point is around 5 degrees, and look at the melting point of this one. It's like negative 93 degrees. So what is going on there? So on this one, it has to do with the shape. So when you look at benzene, I'm going to attempt to draw these little hexagons. But benzene can slide in together, and it can have a lot of touching in the surface area of how the solid fits together. And when you look at the toluene, it has this little side group that gets in the way of it fitting together. And so because it can't fit together as closely, then it's easier to rip it apart. So those dispersion forces is all we have here. Where in our first example, they can fit very closely together. In our second example, they can't fit as closely together. So we get a much stronger dispersion force in the first instance with the benzene, and not as much in the toluene. So it's easier to rip it apart. And that's reflected in the boiling point. All right, so I have three molecules here. Can you predict which molecule will have the highest boiling point and which will have the lowest boiling point? We can compare these because they're about the same size, and really we have the same carbon chain. We've just added a few things to it. So stop the video and see if you can figure it out. Okay, we're back. So when we look at each of these molecules, let's go through and identify if they're polar or nonpolar. And so on this first one, we look, there's that little OH group. This is polar. And this second one, we only have carbon and hydrogen. And remember, carbon hydrogen is a nonpolar bond. So this is a molecule that's just full of nonpolar bonds. And let's look at this last one. So this last one, we have that carbon oxygen group. And so this would be polar. Okay, so again, it's not carbon and hydrogen, and it's not bonded to itself, and it's if it's not carbon and hydrogen or bonded to itself, then that bond is polar. Okay, so looking at these, we can double check the polar ones and see if they have hydrogen bonding. And on the first one, we find that it does have hydrogen bonding. That last one, there's no hydrogen bonding, just it's polar, so we just have dipole-dipole forces. So which one's going to have the highest boiling point? So that would be this one. So this one would be the highest. And which one's going to have the lowest? That would be the middle one. And the last one there, the 3-hexanone, that would be somewhere in between. So let's see how we did. Let's look at the answers when it boils. And you see that we are correct. So that first one boils at 135 degrees, and the middle one boils at 69 degrees. All right, let's look at this one. So we want to compare carbon tetrafluoride, carbon tetrachloride, and ammonia. So let's look at their boiling points. We can look these up. So carbon tetrafluoride boils at minus 128 degrees. Carbon tetrachloride boils at 76 degrees. And we have ammonia boiling at negative 34.4 degrees. So go ahead and stop the video, identify it's polar, if it's nonpolar, what are those intermolecular forces, is there any hydrogen bonding, and then we'll come back and discuss the answers. Okay, we're back. So let's look at that first one. And that first one, we find that it is nonpolar. So we have around carbon, we have a fluorine or carbon tetrafluoride, and it's the same bond all the way around. I didn't draw the dots, but they are all there on the fluorines. There should be 6. So it is nonpolar, so the only thing that we have there is dispersion forces. And let's look at the next one. So carbon tetrachloride is the same thing, a carbon with 4 chlorines all the way around. And it is also nonpolar because it's symmetrical, the same bond all the way around. We only have dispersion forces. And let's look at the last one, ammonia. So ammonia, it is trigonal pyramidal. And because it has those unbonded electrons, this is always polar. All right. So being polar, it will have dispersion forces, as all things do. And being polar, it will have dipole-dipole. And then if it's dipole-dipole, you should always check and see if it has hydrogen bonding. And it does have hydrogen bonding because we have a nitrogen-hydrogen bond here. So there's that little bare naked proton hanging out with that hydrogen. And so we do have hydrogen bonding. So let's look at the data and figure out what's going on here. So let's compare the first 2 molecules. So we have carbon tetrafluoride. And some people think, hey, that there's hydrogen bonding there, but it's nonpolar. If it's nonpolar, there's no way you have hydrogen bonding. Also, notice the fluorine is not bonded to a hydrogen, so it's just bonded to carbon. So no hydrogen bonding there. So we can see that the forces are a lot weaker than that carbon tetrachloride. So the one that has the chlorine. In fact, it's pretty dramatic. We're comparing a negative 128 to a 76.5. So what's going on there? So there's only dispersion forces, so we're looking at a difference here of polarizability. So chlorine has more electrons than fluorine. So chlorine only has 17 electrons, and fluorine only has 9. So chlorine has a lot more. So those dispersion forces can really shift and create those temporary dipoles to hold it together as a liquid. And so to go in and break it, it's going to take a lot of energy. Now compare that carbon tetrachloride to the ammonia, that last one there. It's polar and it has hydrogen bonding, but it doesn't come anywhere near to the boiling point, to that 76.5 degree boiling point. So here's a case where the dispersion forces all add up to be stronger than something that is hydrogen bonded. So you can say that hydrogen bonding is the strongest bond if you have molecules that are the same size. But carbon tetrachloride is much, much bigger than ammonia. Ammonia is really tiny. And so that's why the boiling point is so higher, because it has a greater polarizability in that carbon tetrachloride. So just because it has hydrogen bonding doesn't mean it's going to be the strongest intermolecular force when you're looking at a set. But you would have to be given the boiling point so that you could compare.